For this video, let's try to prove this identity for differential equations, or the derivative for complex numbers. This is also true for the derivative of any function expressed as z to the power of n in the real number system. But since we are now in complex number system, let's also show this to be true. We are told here that our function is z to the power of n. Okay, it's any form of z to the power of n where n is any exponent. Okay, this is just equivalent to this form here, and that is what we're going to prove for this video. Now, let us use here the definition so that when after proving this, we can apply the same concept or differential or the rule in differentiating other functions later on. Let's have the definition for the derivative, which is equivalent to the limit of your f of z plus delta z minus f of z all over your delta z as your delta z approaches 0. What we need to do here later on is identify the equivalent form of this function from this f of z given as z to the power of n, and later on apply some processes in order for us to cancel this because we don't want 0 as our denominator. Allow me to use a portion here of our scratch. We know that our function is z to the power of n, and our function of z plus delta z is equivalent to, or let us place it here, equivalent to z plus delta z to the power of n. This is what we're going to apply later on in our given limit here. So we'll be using this and that, and hopefully we could apply some process as well. So this is what will happen here. The limit, the first form is, you have here z plus delta z raised to the power of n, okay, minus f of z all over, your f of z is actually z to the power of n, right? Z to the power of n. Then you will have here over delta z as delta z approaches 0. Okay, now notice our n is not given. My point exactly is here. So we don't know the exact expansion of that, because if it's squared, so we have a square of a binomial. If it's cubed, we also have the cube of a binomial. If we're going to have even exact value of, let's say, 15, we can use the Pascal's triangle or the binomial theorem in order for us to give the exact value for that. But this time it's n, meaning we have n plus 1 possible number of terms. So how what can be done here in order for us to move forward and hopefully target this item here? Now, let's move back here. Okay, so again, when we talk about squaring that, okay, we are going to follow the Pascal's triangle, right? 1, 1, 1, 2, 1. This row here provided us with z squared plus twice z delta z, and you have here plus the square of your delta z. If you will have z plus delta z cubed, of course, according to this Pascal's triangle, you will have here z cubed plus a 3z squared. Take note that you will have decreasing power of your first term and increasing power of your second term. So you have delta, that's an x, delta z plus 3z, the square of delta z, plus the cube of delta z, and so on and so forth. But what will happen if it's n? Okay, what will happen if it's n here? You would like it to be integrated to this proof. Now, if we're going to extend that, we will have here z plus delta z raised to the power of n. This actually using, okay, moving here, so on and so forth, and for that, this is actually equivalent to z to the power of n. Okay, plus you will have here. You may also review your combinatorics for this, because aside from the Pascal's triangle, we can use the binomial theorem. The coefficient for the second term is actually identified as the combination of n taken 1. Okay, because earlier it was n taken 0. Okay, here, okay, you will have here n taken 0 and z to the power of n. Then you will have n taken 1, and you will have here z to the power of n minus 1, and then you have delta z to the power of 1. Then plus, you have n taken 2, z to the power of n minus 2, and you will have here delta z to the power of 2. Because the binomial theorem for this is actually equivalent to this form, the summation of n taken k. Okay? Then you have here the first term, n minus k, and then your second term to the power of your k. Let me separate this here. Okay? So as your n, or I mean your k, starts with 0 until n. So we'll have here plus until you will reach a certain point here with you will have your n taken, so that's plus, right? N taken n minus 1, right? And you will have here z to the power of n minus n minus 1, or we'll have here power of 1 already, z to the power of 1, and you have here delta z to the power of n minus 1, and plus n taken n, z to the power of 0, or just simply 1, and then you will have here delta z to the power of your n. Okay, so all of these are part of this expansion using the binomial theorem. Now it's very long, right? But of course, that's its equivalence. So we're going to apply that here. Okay, so we have here the limit. Take note, we might just use, if it's okay with you, yeah, this five elements. So you will have here this actually z to the power of n plus, because n taken 0 is just 1, okay? So we have n taken 1, okay, it's actually z to the power of n minus 1, and then we have your delta z. Then plus, you will have here n taken 2, z to the power of n minus 2, and the square of delta z. Plus, again, you will reach here your second to the last element, n taken n minus 1, you will have here z and your delta z raised to the power of n minus 1, and then you have here plus n taken n delta z raised to n. Okay, yeah, so that's it for this form alone. But take note, you will still have here, allow me to write it here, minus z to the power of n, this item, and they are all over, okay, your delta z as delta z approaches 0. Okay, now again, n is not defined, that's why, I mean, n is defined, but n is not exact, so we will have that form. Don't worry about that. We are all going towards our goal. So we will have here the limit of your delta z approaches 0. Take note of this. This is to be removed with that. Z to the power of n minus z to the power of n here. Okay? And allow me to factor all these delta z's here, because the goal is to cancel that, right? So when we factor delta z, allow me to move all of this at the bottom. Pardon. Or remove this. Allow me to remove this. Okay? Right. With that. So we're going to factor delta z. So what remains for our first term is n taken 1, which is equal to n. Okay? And z to the power of n minus 1. Or again, let me move it down. I mean, sorry for that. Let me erase all of this to make it clear. You have here the limit. Delta z approaches 0. So that's again, z to the power of n minus z to the power of n is already gone. N taken 1 is just n. Z to the power of n minus 1. Sorry, we factored, by the way, forgot. We factored delta z. That's why your first term, your second term now is n taken 1, or n as mentioned, okay, times your n, z to the power of n minus 1. When you take out here as delta z, you will still have there n taken 2, z to the power of n minus 2, and delta z. Plus, if you're going to take out here another delta z, so what will happen there is actually, okay, n taken n minus 1, z, and you have here delta z, n minus 2 now because you took out 1 as you factored it here. And finally, for the last term, is just n taken n, And since this was n earlier, you will have here delta z raised to the power of n minus 1. They're all over delta z. Now this time, we can cancel that, and we are now guaranteed to have a denominator that will no longer be 0. Okay, so allow me to also erase some of this again, leaving the binomial theorem alone. Pardon for that. You can of course review the portions earlier of the video for discussion of those items I've erased here. So what needs to be done here is automatically listing the limit as delta z approaches 0. So you have here n z n minus 1 plus n taken to z n minus 2, right, times delta z plus dot 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 plus n taken n minus 1 z delta z raised to the power of n minus 2 and plus n taken n delta z n minus 1. We don't have a denominator anymore, so we can just automatically substitute this. And take note, from here to there, all of them have delta z in their term. Delta z here, delta z, and of course all the terms here as well. That is because when you look at your expansion earlier, okay, the exponent for your delta z will just increase from 1, 2, and then of course you will have 3, and you have n minus 1 before you reach n. So you're expecting that all the terms in this ellipsis here contains delta z, which is also true to this one. Once you substitute delta z approaching 0, what you will have here is simply n times z to the power of n minus 1 plus 0 plus 0 plus dot 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 0 to 0, leaving the final result to be n, okay, n times z to the power of n minus 1. And what is this? This is actually the intended equivalent for the derivative of z to the power of n. N times z to the power of n minus 1. And with this now, together with the binomial theorem, we're able to show that the derivative, okay, of our z to the power of n is just equivalent to n times z to the power of n minus 1. Okay, that is the rule for differentiating this type of function. Again, you will try to review all of these things together with some items I have erased here, because I will no longer return to that as I have a lot of things I have already written here. Thank you very much for watching.